Okay. So what about the effect? Okay, sorry for the cut. I got my tongue wrapped around itself trying to explain what was happening on this slide previously, so we'll take another stab at it. Okay, so we want to consider the effect of pressure on both craze yielding and shear banding. So imagine we have a stress state, a pure tensile stress state, right, in 2 dimensions. So we have on the diagonal sigma 1 and sigma 2, right, and they're both equal. So we're on this line. And sigma 3 is 0, right? So sigma 1 and sigma 2 are positive. So what's going to happen when we add a negative sigma 3 component to it? So we add something that's compressive in the sigma 3 direction. Well, so remember the hydrostatic pressure is the trace of our stress divided by 3. So if we add a negative sigma 3 component to it, we're reducing the hydrostatic pressure on our sample. Right? If we reduce the hydrostatic pressure, it makes it's going to create more free volume and make shear banding easier. So our yield surface is going to shift this way. Now, if we're compressive and sigma 1 and sigma 2 are negative, and we add a third negative component, it's going to decrease our free volume even more, right? So our surface is going to shift this way. The pressure has a greater effect on craze yielding, right? So if we add a triaxial stress state, if we add a negative sigma 3 component, we're really opening up a lot more free volume, right? And we can craze much easier, right? And in fact, without the addition of too much of a sigma 3 term, remember we're talking a negative term, so we're reducing the hydrostatic pressure, we can actually move the craze yield surface completely outside of the shear yield surface. So that means we will always fail by shear banding rather than fail by crazing. Okay? Play with this a little bit. Think about it from a mechanistic point of view as to what's happening. Okay, and to wrap it up, we want to talk about deformation of semicrystalline polymers. So remember, back at when we talked about viscoelasticity, we talked about the structure of polymers, right? And we said we can get semicrystalline by arranging. This is polyethylene. The chains in this way, and we get a unit cell here, right? And remember, we have an inherent anisotropy in our crystal properties because along this direction we're pulling along the carbon-carbon backbone. Along this direction we're pulling on the van der Waals forces that hold these chains in alignment. So we can't get a cubic polymer crystal because of the differences in bonding. Right, and these chains tend to fold back and forth, and you get these lamellar-like crystalline regions here. And we've got a whole bunch of defects, amorphous regions. We can have dislocations in our crystalline regions. We can have a whole bunch of other defects, imperfect fibrils, folding errors, amorphous regions that have short-range order, like the crystal highly correlated short-range order. But this is just kind of a reminder of the structure. So when we deform semicrystalline polymers, this is nylon 6,6, the most common nylon, right? We have a we see behavior that looks like this. We have an initial yield and then a softening, and then a hardening behavior, right? And so this here, this region here corresponds to drawing. So here we have the highly oriented chains. So this is initial yielding. This is our drawing regime. And then this big increase here corresponds to when you are pulling on the elongation of the aligned molecular uh, structure. Right? And so for polyethylene, you can draw out to very, very high strains before you get to there. So this is out to a strain of 30, and we still haven't gotten to the stage 4, where we're pulling against the perfectly aligned structure, deforming the perfectly aligned structure. So schematically, what happens? Here's our crystalline regions, here's our amorphous regions. So as we pull, the amorphous regions basically stretch out, right? And they can't become fully elongated because there's cross-linking and other types of entanglements happening, right? But they stretch out, and if we keep pulling, the crystalline regions will break up by shear. Remember, these crystals are very strong this way, but this way they're only held together by van der Waals forces. And by doing that, it allows the amorphous region to stretch out even more. Right? So these are basically the stages of deformation in a semicrystalline polymer. So here we are in our highly oriented structure. Right? And we can also get, right, they're crystals, right? So we have defects. We can get slip in polymers, right? So we can get crystal shearing, right, which can give us stacking faults in our crystal. Here we can see we've got these folded regions, right? It'll be very hard to shear along this way because these folded regions get in the way. But if we have a region where we don't have a lot of folding, these crystallites can break up along this line here. And again, this is a schematic picture, but you can use it as kind of an internal mental model of what's happening in the polymer. Right? And so here is PTFE Teflon, right, with large crystalline regions. So this is a replica surface that we're looking at here. So what this is a surface, and then this is basically a carbon mold made to the surface. This carbon mold is then put in the electron microscope and to image it, because being non-conductive, it's hard to get good images of the polymer surface without having lots of charging. So the classic old way of doing it before things like environmental microscopes were invented was to make replicas of the surface. And you can see the alignment in the crystalline regions. Right, you can see the extent of the crystalline regions and amorphous regions. Now here they've deformed to a plastic strain of 70%, and you can see that the crystallites have fragmented basically. They're not extended crystalline regions like you see here, and you can also see what are potentially slip traces in the crystalline regions. Okay? And as we draw, right? So when you start out, the polymer is basically going to be pretty isotropic. So lambda of 1 is this curve here. This is the modulus along the x direction, the modulus along the y direction, modulus along the draw direction. Right? And as you increase, you develop anisotropy. Right? Your chains become very highly oriented. So you get a much stiffer along the drawing direction than along other directions. Now something curious happens here, right? Notice initially, when we first begin to draw, we go from an extension ratio of 1, which means no deformation, extension ratio of 1.4, which is basically about a 40% strain. We've weakened our elastic stiffness, and then it starts to get higher. Right? We've weakened in all directions at 1.4. By the time we're at 2.4, we've exceeded along the drawing direction and the perpendicular direction, but at a 45-degree angle, we're significantly weaker than where we started. Then by the time we get out to 4.6, we've got a lot more strength along the, a lot more stiffness along the drawing and perpendicular direction, but a lot weaker at a 45. So this is something I want you guys to think about. What's going on here? Why does it follow this pattern? Right, and we'll talk about that in class. Okay, take care. Have a good week and weekend, and we'll catch back up with more lectures next week.